Okay, hey everybody. So we had lecture today, and I said that I would do an example on doing linear interpolation within a triangle. And so here is, and I said I might do it on a piece of paper, but my handwriting's so bad, so I'm doing it with ASCII art in VI. And so then here's our triangle. There's three vertices, V1, V2, and V3. For each of the three triangles, we have a location. So V1 is at the location x equals 2.5, y equals 4.5. V2 is at x equals 1.5, y equals 2. And V3 is at x equals 3.5, y equals 2 as well. So V2 and V3 are at the same height, even though one is shifted over the other. And so I guess the origin would be like, I don't know, here. Um, so because they're not at the origin. And then there's a field value for each. The field value for F1 is 3. The field value the field value for V1 is 3. The field value for V2 is 0, and the field value for V3 is 1. And then we'd like to understand the field value for some V4. And I'm telling you V4 is at the location x equals 2.25, y equals 2.75, and we don't know its field value. And so the game plan is going to be to calculate the location and field value of some V5 and V6. And so V5 is at some x location and y equals 2.75, and it has a field value of something we don't know. And similarly, V6 will be at some x location, again a field value we don't know. And so in terms of the x location, I'm actually going to solve that again with linear interpolation. So not using what we did before, which was calculating the slope of the line y equals mx plus b, but instead I can just again do lerping. Here's our lerping slide, linear interpolation. And so we can calculate a t, and so we're going to say t equals, and here's the t, x minus a over b minus a. In this case, we're talking about it with respect to y, and so a is at y equals 2, and b is at y equals 0.5, and x is at 2.75. So we say 2.75 minus 2 over 4.5 minus 2, and that's going to give us a proportion. And so I'll go in Python, I'll say 0.75 divided by 2.5, a proportion of 0.3. And then what is the x location? Well, that means the x location at V5 is equal to the x location at V2, which is 1.5, plus 0.3 times 2.5 minus 1.5. And so that's going to end up being, and so here I'm taking this formula, and the field that I'm evaluating is the x field. And if that doesn't make sense to you, no problem, just do it the way we did it before. And so this would be, looks like 1.8. And then we also need to calculate, so that's the x value. So now we can go to V5 and say it's at the location of 1.8 and 2.75. And then we're going to do it again for the field value. And in that case, we're going to say the field value at V5 is equal to, again, it's going to be f of a plus t times f of b minus f of a. And in this case, the field value is going to be f. So it would be 0 plus 0.3 times 3 minus 0 is going to be 0.9. So now we've got V5 all figured. Its x location is 1.8. We already set the y location to be 2.75, and its field value is 0.9. And then I'm going to do it again for x of V6, and that's going to be, let's see, f of a. So we'll set a to be V3, so 3.5 plus 0.3. It's going to be the same t value, because 2.75 minus 2 is 0.75 divided by 2.5, which is 4.5 minus 2, is 0.3. But now it's going to be 3.5 minus 2.5. And so that would be, I guess, 3.2. That seems right, yeah. So now we've got that V6 is going to be at 3.2. And when we calculate the field value for V6, it's going to be, again, f of a. And in this case now the field we're evaluating is f. And that's going to be 1 plus 0.3 times 3 minus 1. And so that looks like it's going to be 1.6. Okay, so now we've successfully calculated the locations and the field values for V5 and V6, and then we're just going to do it again along a scan line, along our y equals 2.75 line. I guess if we're really doing scan lines, we would always be doing integers and never fractional numbers like 2.75. Whoops. But it still works, and we can interpolate to anywhere along the triangle, and so interpolating 2.75 is fine. Again, like I just said, in your code, it will always be on scan lines, so it will be on even integers. And so then the first thing we'll do is we can calculate the x value at V4 is going to be equal to 1.8 plus, and then I guess we need to calculate the t. Oh, we already know that. Yeah, so it's we already know the x value. The x value for V4 is 2.25. So all we have to calculate is the field value. So the field value at V4 is equal to the field value at V5 plus t times the field value at V6 minus the field value at V5. And so the question is, what is t? Well, t is equal to the x coordinate, because now we're doing an interpolation, a lerp, along that dimension. So it would be 2.25 minus 1.8 over 3.2 minus 1.8 is equal to 0.5 divided by 1.4. We'll use Python for that. Is equal to approximately 0.32. Of course, don't do approximately in your code. And so then we'll say that, oops, sorry, my caps lock went on. Okay. And so then we'll say that f of V4 is equal to f of V5, which is 0.9, plus t times 1.6 minus 0.9. So that's going to be times 0.7 plus 0.9. And so our field value is going to be 1.125. So that's it. We just used this formula for linear interpolation. Again, we used it in a new way to calculate the x locations for V5 and V6, and then we used it in the way that makes the most sense from the slides to calculate the field locations. And then once we had the field values at those locations, and once we had the field values, then we're able to do it a third time to calculate the field value at V4. I hope this was helpful, and also I hope I got it right. So if anyone thinks there's an error in my math, please let me know. Okay, see you all on Thursday.